is something that holds a surface of a fluid together. And in this example, we're talking about a bubble. So I asked my daughter what holds a bubble together, and she said that there's some kind of force on the outside trying to smush it, but there has to be some kind of thing on the inside trying to blow it back up like a balloon. And she's right. So she also said there's something about gravity holding it together, which is not true, but that's okay. The point is, we have to think about what these forces are. And this question right here, what happens if the outside pressure is larger than the inside pressure? Well, hopefully, like my daughter, you think about that and realize that if the outside pressure is larger than the inside, it's going to go. So if you have a balloon that's blown up over time, the inside pressure decreases as air slowly diffuses through it and it shrinks in size. There's a force on the outside pulling it in. That's from the balloon being elastic. And then the force on the outside from the increased pressure inside, which is higher than ambient pressure, which holds it out. Okay? So this shows a picture of this bubble we're talking about. And if we slice it exactly in the center, what you can do is you can take this area here, because that area is where the force is effectively being applied. And you can also say there is this, a circle, and then times sigma, which is some kind of force per length. So if you multiply sigma, force per length, times 2 pi r, which is the circumference, that's the total force holding it together. And anywhere you split the bubble, you're going to get that exact same value. Now, talking about the force on the inside, we will do that on the next slide, I think. If not, I'll have to just say it when we get there. All right, so here we can see that the force is just this. It's the change in pressure, so the gauge pressure from the inside to the outside times pi r squared. Now why is it pi r squared? It's because if you were to look at the hemisphere from the side, you would see that the force is like this on the inside, right? It's supposed to be uniform and going all the way around the bubble. So it's evenly distributed around that bubble. But if we're going to do some trig, you'd see that this one down here, this part, and this part almost completely cancel out. And if I'd done it exactly right and it was a half circle, they would cancel out completely. So it's only the components going to the right in this specific picture. It's only the ones going this direction that matter. Okay? And when you do the trig, you end up saying, it's just delta P times that circle, pi r squared. That's all that's left. So that's this right here. That's the net force trying to push it apart. And therefore, we have to have that exact same force trying to hold it together, which we already said is this. And that tells us what the surface tension is per length. So this right here, that's newtons per meter. And that we can calculate based on this, if we know the difference in pressure, or if we know what the value of that is for a particular liquid, then we can calculate the delta P for that bubble, because the bubble can just shrink until it reaches the proper delta P. All right. So this shows something that you've probably seen in the chemistry lab. If you have a graduated cylinder and you have fluid in it, you get that nice meniscus, right? And you're probably used to seeing that. So that is something like it's shown over here, where it goes up on the sides. And what that is there's an actual force pulling up on the edge of the liquid because there's adhesion between the liquid and the tube, these capillary tubes, whatever they're made out of. So it depends what it's made out of, whether there's adhesion or some kind of repulsion. So in this case, we have adhesion on the left. And if we were to draw a vector on the edge of it, we would get something like this. This vector going up, which is equal to the angle we have right at the edge of that meniscus. And we end up having a vertical component here, and we have this horizontal component here. Now the horizontal component is canceled out all the way around the circle, but the vertical component is not canceled out from the force from surface tension. Okay? Probably need to spell some things correctly. And so where is this force actually being applied? It's being applied around the circle. So if you look down at the top of the tube, you have this force coming out like this, where the adhesion on the edge of the liquid and the tube is providing that force. Okay, so this over here on the right side, this over here is just one side of that capillary tube. Okay, so that adhesion has this force going up, and since it goes around a circle, we can multiply it times 2 pi r right here. And this cosine theta, hopefully you see, comes from this angle we have over here. If we do cosine theta, then we end up getting the vertical component. That's what's holding it up. The vertical component per length times the total length gives us the force holding up that fluid. And then we have to say, well, that's going to be equal to whatever the force is trying to push down the fluid. And that force is shown over here. Now this is how you might often see this equation if it was written in a textbook. I don't actually know where my fluids textbook is from college, but probably said something like this. Not 100% sure, but it's pretty likely. And the question you should ask yourself is, what is that? What is that gamma? Does that have something to do with the speed of light? No, that has nothing to do with that. We just have so many Greek letters. And personally, I find it a lot easier if we replace that gamma instead with this, rho g. Because now we just have rho gh, which you're familiar with, times pi r squared. And what is that? That's volume times mass per volume times the acceleration due to gravity. That's a force. That's simple. So on this slide, we're showing the exact same thing, except this time we're showing it as rho gh. So hopefully that makes sense to you. And this is just saying that because of that adhesion to the surface, the liquid will rise up the capillary tube if it's attracted, or a beaker or whatever, right? On the edges, it'll rise up some amount, and we can actually calculate that amount. And then what if it's repelled by that? So in this side, this one over here, right? This here, this is showing some repulsion. So if you could imagine, I'm not sure if you can imagine this, but if you imagined this being up above it looking like that, that would be some kind of repulsion. But if you have repulsion, it's going to pull it down. So it doesn't end up above with a flipped over upside down frowny face, right? It pushes it down. And we get the exact same result, right? If you think about it from a buoyant force perspective, it's basically the exact same thing, right? We're replacing what would be mercury with air. So the mercury wants to push it back up, but the capillary repulsion pulls it down, and our equation is basically exactly the same thing.